variables, these quantities, so wall screen friction coefficient, and also the law of the wall. So what we need to do here is to, first of all, we need to plot the for this screen friction coefficient CF. This is the equation. So we need the rho infinite to u infinite. Okay, this we can calculate it later. And then the wall shear stress. The wall shear stress can be calculated in this way. So with the cell, the closest cell to the wall, or in a more convenient way, Fluent has the wall shear stress as a quantity already in the post-process quantities. So what we can do is we want the wall shear stress along the plate. So in plots, you can expand plots. There is XY plot. You can double click. So this allows us to plot some quantities over lines typically. So we need, first of all, we need a line. And we can create a line using no surface on the bottom. And then there is the option line break. So a new surface name, we can set this like center line. And this is the line that goes from the center of our domain along parallel to the plate. So this has, we need to set the coordinates for the endpoints. So we need first of all to know the coordinates, let's say, of the point here in the middle. In order to do that, we need to know what are the size of the domain. You can find that in scale on the top here in the tab domain scale. So these are the minimum x, y, and z values of our domain extent. So the middle y in this case is minus 0.5. So we can set both y's as minus 0.5. The x goes from minus 0.33 to 2, but the part that we are interested in, so that is the non-strip wall, start at x equal to 0. So we set x0 equal to 0, and x1, that is the other endpoint, equal to 2, to the maximum extent. Z is the distance from the plate, is in that direction. So we need the wall shear stress, of course, on the plate, so that has to be equal to 0. So we can create this line and close. Now in this XY still tab, we can plot XY plot center line. I call it like that. You have some options. The first option is not values, and this is asking you whether you want the values that you are plotting at each cell point, like at each node of the grid, or you prefer that is also interpolated between the cells. It depends on the cases. For this case, I typically don't select that. And then the position on x-axis, we can keep that. So this is asking you in which direction you want to plot your quantity. So in our case, in the x direction, so that's okay. And then we can also order points. That means that the points will be ordered for the x coordinate. So we have an increasing x coordinate for each point, in case the solver is reading them in a different order. Okay, so then we can plot the wall shear stress. So we can do that in y-axis function. We change that to wall fluxes. And in wall fluxes, here you have the wall shear stress. So you can select in the surfaces the center line that we created before and save plot. If you do that, you can see that now you have the wall shear stress along the x-axis, so along the plate. So in x equal to 0, so the beginning of the plate, you have very high wall shear stress, and then it's decreasing as the turbulent boundary layer is increasing in size. We need also post-process of this, so we can actually save this file. And we can do that always in this window. You can use write to file. If you select that, there instead of save plot, now you have this write. So now we are in the working directory, the working folder, and we can save this this distribution. So tau wall shear stress over x, and we call it tau underscore w, so tau wall. And you also need to add .xy, this is the format, and you need to insert it here, .xy. Okay, so now in my working folder I'll have an XY file that you can open like a text file, where you have the distribution of the wall shear stress. Okay, and then next also what we need is, since we need to calculate this quantity, the wall skin friction coefficient for Reynolds theta. Reynolds theta depends on theta, and theta is the displacement thickness. And in order to calculate the displacement thickness, we need to know the distribution of density and velocity in the boundary layer. The density is constant, almost, since this case is incompressible. Instead, we have a variation of u as a function of y along the boundary layer. So what we will do is to create a series of lines in the domain. We have, for example, lines like in this direction, so perpendicular to the plate, at x equal to 0.1. We create another one at 0.2, 0.4, 0.6, and then you also have 1 and 1.5. So we create several lines where then we can plot or extract the flow quantities all over these lines. So this is for our center line. We can close that. And we can create a new plot. So if you double click on XY plot, here again, you'll get a new window. So in this case, once again, I deselect node values. In this case, the position on the x-axis, we can deselect that also. Now that we are selecting which variable we want on our abscissa. And I keep that ordered points still on. So what we need to do now is to create those lines. So we can do that in new surfaces, line rate, and then we need to set them like this. So our endpoints will be, here we have x minus 0.5, so we are in the center of the domain in y direction, and 0, so we are starting from, this actually is not y, in this case it's z, the direction perpendicular to the wall, so that's 0, this is 0.1, and then instead 0.2 will be again x, so 0.1, 0.2 until 1.5, the same y, so in the center of the domain, but in this case we need to choose a z value that is covering at least the boundary layer, all the boundary layer. So with 0.1 we are already fine. We can check them later when we plot the line. So for example, for the first point, we can call this line 0, 1. That means this is the y for x equal to 0.1. So we set x0 and x1 equal to 0.1. y0 is minus 0.5. y1 also minus 0.5. z0 is 0, close to the wall, and here we set 0.1 and create. So now we have this line over here, line 01. To check if we have done things correctly, what we can do is, I keep this open. So in general, if you click on general, display, you can actually display the line 1, for example, and the plate surface. So this is the plate and this is the line perpendicular to the wall that we created. As you can see, when you hit create, it's not closing this window, but instead it's like reinitializing it. So now you can create a new surface. So we can call this line 02. So for x equal to 0.2. And we just need to change the x0 to 0.2 and create. Then we do the same for 04. So we set these values to 0.4, 06, and create. Then we have x equal 1, so let's say it's 10, 1.0. So x0 equal 1, x1 equal 1, and create. And finally, 15, so 1.5, so x0 equal to 1.5 and x1 equal to 1.5, and create. Once I've done that, I can close this window. Again, in display here, I can plot all of these lines, for example, to check that they are good, they are correct. So I'm covering all the good resolution our domain, our plate. So we need to plot the flow quantities all over these lines now. Okay, so I can close this mesh display. And in this XY plot, now I can plot on the y-axis, for example, the velocity. So I can see the velocity distribution along these lines. And on the x-axis, that's the z coordinate, so the coordinate perpendicular to the plate. So instead of pressure, I can choose mesh. And then in mesh you have x coordinate, y coordinate, and z coordinate. So if I select that, then I can select the surfaces. So I want all these lines I created from line 01 to line 15. If I save now, save plot, this is what I have. So this is the velocity distributions versus the coordinate perpendicular to the wall. So at line 01, that's the first curve, and then at line 15, this is the velocity distribution that we have. So these are the velocity distribution at those lines, and we need them to calculate this integral. Because in this case, for this equation, we need u as a function of y that for our simulation is z. So that y is the distance from the wall. So we can post-process them in Excel. So we can write to file. Then we have the option write. And here I can call this v.xy. And hit OK. So for post-processing, you would actually need also the density distribution, but again, this is incompressible flow. We use a constant value of density. And if you want to check what value of density is used here, I can use the select write to file, select density as a variable, save plot. So you can see that this is basically constant to 1.17. So the range is very small. So then you set it to 1.17. And let's see. Oh no, yeah, there is also another thing. So then you have also this request to plot the eddy viscosity at different locations. This you can do directly in Fluent. So at x equals 0.2, 0.4, and 0.6. So in Fluent, again, I take this plot for the different lines. So we are at 0.2, 4, and 6. And the variable for the eddy viscosity is, you can find it in turbulent viscosity. So that's the eddy viscosity. And you can plot. So now you can see also the distribution of the calculated eddy viscosity as a function of z for these three x locations. Okay, now we have 20 minutes. I can try to show you how to post-process in Excel this data. So in your working folder, now you should have these two files, tau wall xy and vxy, that have the distributions of wall shear stress and velocity. For those, the wall shear stress was calculated for the center line, and the velocities for the lines perpendicular to the plane. So I open Excel. New workbook. And I can copy the values of tau wall, so these two columns, Control A, Control C, Control V. And I can do the same for the velocity. distributions. So I open this text file, Control A, Control C, Control V, but I need an additional step here because now I'm plotting this velocity distribution initially for line 0, 1, and then I can find the other variables, other velocities at different locations down here in the Excel, so I can move this on the top. I could do that with Control X, so I cut and then copy them on the top. And you can do the same for these lines 0, 4. Then you have 0, 6. Ten. And 1.5. So we have here the velocity distributions, and you can see that the first column for all of this is the distance from the wall. Yes, please.
I'm sorry, can you show once again how you've done to obtain this file?
Yes. So in Fluent, you can opening the XY plot. I was deselecting the node values. In this case, also the position on x-axis, I was deselecting this option. And if you have created these lines, so you can just select the lines where you want to save your flow quantities. So then in y x function, here you can select the velocity. So that's the velocity magnitude. And the x-axis function, so where you want to plot them on, is the z coordinate. So you select, you change from pressure, you go to mesh, and the mesh you need to select z coordinate. That is the coordinate perpendicular to the plate. So if I save plot this now, I get this distribution. So they are correct. So then I select this write to file, and then I can write them. And I call them v.xy. And some text files that I can copy in Excel. So as I was mentioning, the z coordinates, so the distances from the wall are the same for all the lines, so we can get rid of them. So I will delete these columns. I'll keep only the first one, in a way that here then I can have this, let's say our z, or let's call it y, that is distance from the wall, to be coherent with the text of the exercise, and here it's the v for 0, 1, so for x equal to 0, 1. Then I can put them all together. This is v for 0.2, velocity for location 0.4, v for 0.6, 1, and 1.5. then I can delete the three first lines. Here instead we have, this is our x value, and this is our tau wall. Okay, so what we can do, first of all, we can calculate the infinite values. So you can see, for example, in the definition of Reynolds, we have rho infinite, mu infinite, mu infinite. That is the free stream conditions for each line. So basically, the value that we have further away from the plate. So at this location, let's say at the further location. So let's set here x equal to 0.1, 0.2, 0.4, 0.6, 1, 1.5. And then we can calculate, for example, u infinite. So the free stream velocity. We can either take the last point of these columns for each column, for each x location, or we can calculate, for example, the maximum. That's basically the same. So we said that the maximum value of the velocity is the free stream velocity. So for the column related to the velocity of at x equal to 0.1. And okay. If you pull this formula, so the maximum of that column for the other x location, then you get also the other u infinite. They are almost the same. And then we can take also, we need also the rho infinite. We said that this is this can be assumed constant, the value of 1.17 for all the cases. So I set 1.17 for all of them. And then we need dynamic viscosity, also mu infinite. So you can find this value in fluent. In the top here there is materials, air. So we simulated this case with a viscosity. This is the dynamic viscosity, and this is the value. So 1.789 10 to the power of minus 5. So I copy this value in my Excel. And this is also a constant, so it's the same for all the cases. Okay, now what we are missing is, in our Reynolds theta, we know the free stream quantities, we need theta. Theta, we need to solve this integral. So now we are going to calculate d theta right here. For each cell, we calculate the d theta. This is approximately the u as a function of y over u infinite. That's because the rho, we assume the rho constant, so this is 1, this is ratio. Times 1 minus u velocity distribution over y over u infinite. times dy. Or if you prefer, you can get finite steps, so delta theta is equal to delta y. So now we can calculate those delta theta. So I will do it on this column over here. I call this d theta. Again at 0.1. And then I copy these values also 0.2, 0.4, 6, 1, and 1.5. So we need to implement that formula. So that's going to be uy. So which uy? You can use either one of the two extremities point or an average value. So I'll go for an average. So I select this plus this, so the 2 points of my interest over 2. This is uy over u infinite. So the u infinite for x equal to 0.1. This is 68.66 for me. Times 1 minus uy over u infinite, so the same term we have here. So I copy this formula here, closing round brackets, and then times dy. dy is the difference between this y minus the previous one. So the difference between this the y value at this point minus the y value at the previous point. Okay, so this is the formula. If we want to pull it in for different x directions or also for different y directions. Yes?
Do this once again. U infinity. Firstly, v01 minus 02 minus 01. Can you do this again? This
Yes. So the first value here is E2 plus E3 over 2. This is the value of the velocity at the first y plus the value at the second y. So this is the arithmetical average. I get that value.
And then divided by
By L4, that is du infinite. For x equal to 0.1. So I get the values, let's say, at one value here, I get the average, and then I divide them by the value over here.
And then 1 minus.
1 minus the same. So u function of y, so again the average
Okay.
over here. So I'm copying that formula for this and copying,
Okay.
pasting in there. And then delta y, it's the y value over here minus the y value over here. So the higher y minus the lower y.
And why did you decide to do average? Like, is there
Just a choice.
preference?
Just a choice. I mean, you need a value of uy that defines, let's say, that range. So you can either, if the range is very small, you can either take this or something in between. It's fine. And if you want to pull that in the different directions, what you need to do is actually to lock some cells. For example, you can lock the cell related to L4 for me. So this is U infinite. So when I'm pulling on for different axes, I can do that. So I don't need to lock the letter. But when I'm moving that for the Y, I need to lock the number. So if I lock with the dollar the 4, when I'm pulling it on the number, then it doesn't change. I do the same L4 here for the U infinite. And then I need to do it also for the dy. That's the same for all the x's. So I need to lock the letter. So I put a dollar between the letter. So this is my d theta. I can pull it for different axes. So I can double click to check that it's doing things correctly. Yes. And then I can pull it for the numbers up to not the last one, but before the last one. Because if you pull it until the last one, then you can see that here you have a value because you need a cell over here because we are calculating a difference. So then we don't consider that last value. And these are the values of theta. Now, how to calculate theta? It's just a sum. So then, this is the sum of this column for 0.1, and we put it. We don't have time. I don't know if you have further lecture. Probably someone will come anytime soon. I can show you if you want some very quickly how to do to finish this exercise. By the way, you have more than 2 weeks, I think, for this exercise. There is a break in a couple of weeks, and then next week we have a rehearsal on Wednesday morning. The exercise is very similar, so I will show this also in more details next week, but with a different turbulence model. So by the way, we can then once we have theta, we can calculate Reynolds theta using this formulation. So this is the product between rho times u times theta over dynamic viscosity. You can pull this for calculating the Reynolds theta for all the cases. And maybe let's change the format. So let's get to general. Here we needed to plot the Reynolds theta between 4,000 and 13,000. So we are putting that range, we are covering that range. And okay, once we have Reynolds theta, we need to calculate now the skin friction coefficient. For that, we need the tau wall for each location. So here we have the distribution of tau wall for different axes. So we need to get the correct value for the hour x. So for example, the first axis is 0.1. So this is equal to the value of tau wall for x equal to 0.1. So I find on the left column the value closer to 0.1, this one, so I get that value of tau wall. And I do the same for the other. Then I'll show you just for x equal to 0.1, skin friction coefficient. This is equal to, I have the formula here, the ratio between tau wall and the density and velocity. So this is equal to tau wall over 0.5 times rho infinite times u infinite to the power of 2. Okay. So now you have you've done the wall split. You can calculate the wall splitting friction coefficient. You can calculate it for different axes. So now that you have the distribution for different Reynolds theta. And then what you are asked to calculate is y plus and u plus. You can do that with the formula that you know. So you have U distribution, function of y. You know the tau wall for x, for every x, the rho is constant. For y plus, you have the distribution of y. Of course, it's just the distance from the wall. Nu wall, this is just the ratio between the dynamic viscosity that you have over the density. So you can calculate these two values, distribution all over these lines. And what you are asked to do is to plot that value at Reynolds theta equal 10,000. So you have to plot the U plus versus Y plus for Reynolds theta equal 10,000. In our calculation, the Reynolds theta equal 10,000 is approximately at x equal to 0.6, so you can do that at 0.6. Okay, sorry for the rush. I'm not able now to show this calculation. I will do it next week.